Hey folks, welcome back. Mr. G here again. Welcome back to the next in the lecture series for Tech 101 Electric Circuits. Today what we're going to be talking about is the DC voltage supply versus the DC current supply. Basically, a supply of energy to a circuit can be represented as a voltage supply, or it can be represented as a current supply. So what's the difference? Well, think of it like this. If I have a voltage supply in an ideal situation, Vs will appear across this load resistance. It doesn't matter if I change this resistance, the voltage drop across it will always be equal to Vs. So in a DC voltage source, in an ideal DC voltage source, the voltage that applied across the resistor, the load resistor, is going to always be equal to the supply, even if I vary the load condition. So the voltage stays constant even though the load changes. In a current source, in the ideal situation, the current flowing out of the source would be constant even though I was to change the value of the load. So again, in the voltage supply, so in the voltage source, in an ideal situation, a DC voltage source will supply constant voltage to the load even though the load value changes. In a constant current source, current will be supplied to the load will remain constant even though the load changes. So here the voltage remains constant in a voltage supply. Here the current remains constant in a current supply, even though I might vary the load condition. So in this case, the voltage stays constant. Here, the current stays constant. So even though I vary the load, in this particular case, the voltage remains constant. In this particular case, the current remains constant. Two different ways of representing an energy supply, if you will, in electronics. The voltage is much more common, but the current supply does exist in certain criteria and in certain circuits. So it's important that we know both. And moving forward in our course, we're going to look at some theorems that are based around these two things. This one is the basis for what's known as Thevenin's equivalent circuit theory. This one is the basis for Norton's equivalent theory. So as we move forward in our course, both of these become used again. So again, constant voltage versus constant current. You can find information in our textbook. Constant voltage is chapter 8.1 and chapter 8-2 for constant current supply. So again, our textbook, Principles of Electric Circuits, and it's by Floyd and Buckla, and it's 10th edition. So what does this all mean? Well, let's take a look. So first we're going to look at the voltage supply. So we have to understand a concept called ideal versus the practical. Ideal means that in a perfect world, this is what it would look like. In the practical is more real life. So here's what we have. So in the ideal, we have a supply and a load, and that's it. So we have the voltage. Whatever the voltage is being created appears across the load, and that is it. It's as simple as that. In a practical situation, the power supply that we are using. So the actual power supply has components inside it. Those components are represented by a source resistance. So everything inside this black box here, this black dashed line box, everything inside this box represents what's inside our power supply. So of course we have the voltage supply, but then we also have the components that make up the circuit. So in a practical sense, if we looked at this circuit, we can see that Vs will never appear across RL because there's always going to be some voltage drop across this RS. Whereas here, in the ideal box, we have no RS. This is not a real world scenario. This is purely theoretical, where the voltage just appears across the load. Here, inside the black box, we have some components. They are represented by this internal source resistance. According to Kirchhoff's voltage law for a series circuit, it states that voltage drop here and voltage drop here add up to this. So therefore, there's no way that the voltage drop across RL is going to be perfectly equal to Vs, because there's always going to be some kind of voltage drop here. In a real world scenario, what we want to do is we want to make this as insignificant to the circuit as possible. So therefore we want RS to be a lot lower than RL. So we want the ratio of RL to be a lot bigger than RS. Therefore, the majority of the Vs supply is dropped here, and a little tiny bit is going to be lost here. So remember, Vs is equal to the voltage across RS plus the voltage across RL. So by making RS really, 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 really small in comparison, to the big RL, we can get as close to ideal as possible. So let's just do a quick mathematical example. So if I have a circuit, and I'll just show you mathematically, basically, if I had 10 volts and RS and RL. So if we go back to the ideal, doesn't matter what the load resistance is, we're going to get the source voltage across it. In order to make the practical as close as possible, if we varied RL, the voltage across here should not vary that much. So let's try. So what we're going to do is we're going to pick a really small RS value. So let's say RS is 100 milliohms. And RL, for the first example, we will take it as 100 kiloohms. So now what we want to calculate is we want to calculate VRL. So how much of the source is ending up across the load resistor? Well, if you remember from a few lectures ago, we introduced the voltage divider law, and the voltage divider law basically was laid out like this. So the voltage across RL is equal to the voltage supply times RL over RL plus RS. So that's what it came out to be. So let's do the real quick math here and see what we have. So in this first example, it's 10, and we got 100K over 100K plus 100 milli. Let's see what that value works out to be. So we've got 100,000 divided by 100,000 plus 100 milli equals times 10. So we get 9.9999 volts. 9.99 volts. So let's change the value of RL from 100K. So this is the math for the 100K. Let's change it to 10K. So basically it's just going to change this math a little bit, and this becomes 10K divided by 10K plus 100 milli times 10 volts. So it's pretty darn close to the same, but notice that we're losing a few decimal points along the way. So again, it's 9.99 approximately volts. If I then change this value to 5K, so we've got 5K divided by 5K plus 100 milli times 10. And again, we're losing a couple more decimal points. But notice, look, we're still 9.99 volts. Even if we really change that value and we drop down to, let's say, 2K. Let's make it even smaller than that. Let's say 0.2K, so 200 ohms. Let's see what our difference is now. So we've got 200 ohms divided by 200 ohms plus 0.1, so there's 100 milli, equals times 10. Notice that each time we're getting closer to be 9.99. It started off as 9.99999, then it went to 9.999998, and then 999, etc., etc. But we're still at approximately 9.99 volts. So, if we have an internal resistance that is small in comparison to the load, we take our practical source and it will be as close as possible to the ideal source. Again, the ideal source is with no internal stuff, where there's no voltage loss, and what here is showing up here. In this particular case, if RS is small enough, the voltage drop across here becomes very insignificant in comparison to the voltage drop here. So, a practical source with a small internal resistance value becomes very close to the ideal supply. Now moving on to ideal versus practical current sources. Again, we've got our black box theory. So everything inside in the ideal supply, we've got the current source, and that's it. And then we have our load. So everything that's coming from this current source is making it through the load. In our practical version, inside the black box, we have the current source, plus we have, again, internal resistance that make up the components, or represent the components that make up that black box. So we know from Kirchhoff's current law for parallel circuits that when the current leaves the source, some is going to go down there and some is going to go down there. So that we know that I of Rs plus I of RL equals the source current, Is. So again, to make the practical as close to the ideal source as possible, we want to make sure that if we vary the load resistor, the current that makes it to that load resistor does not vary much. It will vary a little bit because, again, we're going to lose some, but we want to keep this as constant as possible even though we change the load. So what we want to do is we want to stop as much of the current from going this way and have more of it going this way. So again, we want to limit how much goes this way, so how much we lose, so that we can maximize how much goes this way so we can retain a large value of current going through that resistor. So basically, in order to do this, RS must be a lot larger this time than RL. So therefore, the current is limited through this branch and flows more through this branch. So we want to make sure that RS is very large in a current source. So again, RS is very large in a current source so that the majority of the current is directed to the load and not down this branch. So again, let's do a mathematical example and see what that looks like. Alright, so here's our example. I've created this little circuit. Got a source current of 100 milliamps. The internal source resistance is going to be 1 mega ohms. The load is going to be 100 ohms. And what we're going to do is use the current divider formula, and we are going to calculate the current through the load when the load is 100 ohms. So the first thing we need to do is we need to calculate what these two things are in parallel. Plug up into that value up there. So we have 1 meg times 100. So I'm using the product over sum rule divided by 1 meg plus 100 equals. So the resistance of these two in parallel is 99.9 ohms. So 99.9 ohms divided by 100 ohms times 100 milliamps. So divided by 100 times 100 milliamps equals 99.9 milliamps. So in this circuit, the current that's flowing through the load is 99.9 milliamps. So let's do the same thing we did with the voltage. Let's change RL. So this is RL is 100 ohms. What if I change RL and RL equals now 1 kilo ohm? So now that becomes, is using the same formula, it's going to become 100 milliamps times these two now in with 1K instead of the 100. And then over RL, so that's going to be 1K. So let's figure that out. So these two in parallel are going to be 1 meg times 1000 divided by 1 meg plus 1000 . So 999 ohms. So then I plug this value into here. I got 999 divided by 1000 times 100 milliamps. And again, I'm getting 99.9 milliamps. So even though I have changed the value here by a factor of 10, I'm still getting roughly the same current flowing. So remember, this was 9, if you looked at the calculator, this was 99.9 something something something. This is 99.9 exact. But again, the concept is we're varying the resistance at the load, but the load current is staying relatively constant as long as we have an RS which is a lot larger than RL. With the voltage source, remember RS had to be a lot smaller than RL. In the current source, RS has to be a lot larger than RL. And that way, we are taking the practical world, real world scenario, and it's able to emulate as close as we can to what the ideal scenario is. Remember, the ideal is whatever current leaves the source goes to the load. Whatever current leaves the source, we want as much of it to go to the load as possible in a real life scenario. So again, in our example here, 100 milliamps leaves the source, 99.9 milliamps makes it to the load. In this condition, I change the load, the same thing happens in this condition. So the two of them actually, and if I did another resistor, another example, again, we would stick with pretty close to 99.9 milliamps making it to the load. As long as the internal source resistance is larger, or quite a bit larger, than the load resistance. So this is ideal versus practical sources, both the voltage and current sources. Sometimes in electronics, you're going to find that you need to convert a voltage supply into a current supply for calculation purposes or to look at it from the current point of view. So it's a very, very easy conversion to go from a practical supply of the voltage type to a practical supply of the current type. RS remains the same. It just changes location. It goes from a series circuit to a parallel circuit. RL remains the same as well. So what we need to do is calculate what IS would be. Ohm's law tells us that IS is equal to VS over RS. So, chapter 8-3 of the book talks about conversions. So current sources to voltage sources to current sources. To convert one into the other. Again, to go from voltage, a voltage source, into a current source, you keep RS the same, you just change its location. Keep RL the same and calculate the new current. So that current is based on this formula, VS over RS gives you IS. Sometimes you want to go from a current source into a voltage source. So again, you want to convert from a current source into a voltage source. The value of source resistance stays the same, it just changes location. The load stays the same. All you need to do now is calculate the voltage for the new supply. And again, that's based on Ohm's law. Voltage is equal to IS times RS for the new voltage. Again, chapter 8-3 of the textbook. So sometimes you want to represent a voltage supply as a current supply and vice versa. So you need to know how to go back and forth from one type of supply to the other. And here is the math. It's as simple as Ohm's law. So again, Ohm's law, calculating the new I. Ohm's law, calculating the new V. So, ideal versus practical, voltage supplies versus current supplies. All of this can be found in chapter 8. So we've got 8-1, 8-2, 8-3 out of our textbook, Principles of Electric Circuits, Conventional Current Flow, from Floyd and Buckla, 10th edition. So that is ideal and practical current and voltage sources. This information will become very important to you in the upcoming theory lectures when we start talking about Thevenin's equivalent circuit theory and Norton's equivalent circuit theory. So this is the background knowledge that you need when you're looking at Thevenin's and Norton's equivalent circuits over the next couple of weeks. So I hope this helps. Until next time, everybody stay safe. Take care.